Okay, hi everyone. Let us start for today. So welcome to the exercise class. Today, the two topics that we're going to discuss are connected to the two exercises in the exercise sheet for this week. And the first exercise explores the notion of precision of clocks, and in particular, will calculate precision for two types of events. And then in the second question, it will also touch the precision, but there we will see if there is a thermodynamic limit on the precision of clocks. And this exercise will combine nicely the things that we've learned from the thermodynamics part of the class and also from clocks and the notions of clocks. Okay, so let us start with the precision of clocks. And so as we've seen in the lecture, one way to describe a clock is to give a probability distribution for the tick of the clock. So, for example, it can be like anything. So, like any probability distribution, suppose like something like this, which essentially gives us the probability of the clock ticking at time t here. Yeah, and this essentially tells us everything about the behavior of such probabilistic clock. And one trivial type of the clock that we can consider is so-called Poisson clock. And for the Poisson clock, this distribution is an exponential distribution. So the probability of a single tick is given by an exponential. So this is Poisson clock. And first we'll look at what is the precision of this clock. So the precision R is defined as mu squared over sigma squared, where mu is the mean of the distribution and sigma squared is the variance. And let me carry out this calculation, which you've probably already done some time back in some probability theory course, but let us repeat it since it's just a simple mathematical exercise. So first we calculate the mean. So this integral we calculate by parts, because we notice that this holds. And then we can write it as lambda t e to the power minus lambda t over minus lambda from 0 to plus infinity minus, you must differentiate the other part of the expression, which gives us 1 because it's t. And we are left with this. The first term gives us 0 because at both limits, the value of this expression is 0. So we are only left with a second term. And this is the integral, like we can calculate easily. At plus infinity is 0, at 0 it's 1 over lambda. Okay, so this was the mean. Now let us calculate the variance. So the variance, sigma squared, as we know, it's the mean value of t squared minus the mean value of t squared. So we need to calculate first the mean value of t squared. So we just write this mean explicitly. And calculating by parts, as previously, we note that we convert to the previous integral, because what we get here is this term calculated at 0 and plus infinity minus so we need to take derivative of t squared, which is 2t, lambda e to the power minus lambda t over minus lambda dt. So the first term gives us 0, and the second term stays, and lambda goes away. So we're left with 2t e to the power minus lambda t dt. Okay, and this is exactly the integral that we were just calculating, just except for the coefficient lambda. So this gives us 2 and 1 over lambda squared. Okay, then we can calculate sigma squared, which will be 2 over lambda squared minus 1 over lambda squared. And we get 1 over lambda squared. Hence the precision R is 1 over lambda squared over 1 over lambda squared equals 1. So the Poisson clock precision is independent of lambda, as we see. So essentially that means that if we take a clock, the probability of tick of which is described by this exponential distribution, we will always have this precision R equaling 1. Okay, now let us imagine a more complicated situation. So suppose that, so here we were only considering a probability distribution of a single tick and the precision of a single tick. What if we want to calculate the probability distribution and then the precision of n ticks? So now we need to calculate the probability of having n ticks after time t, given that all these n ticks are independent. The probability of each single tick is described by this exponential distribution. And yeah, essentially this means that we need to describe the sum of n independent and identically distributed random variables, for each of which we have the same exponential distribution. So here the event that we are waiting for is n ticks at time t. Okay, and how do we calculate such a distribution? So generally, if we have two distributions, let's say P of t and Q of t, and we want to calculate kind of the sum of these two distributions. So the probability at time t for the first tick, for the two ticks happening with these two probability distributions. For this, we need to use something that is called the convolution. So the convolution of two probability distributions gives us the sum of these two distributions. And the convolution is expressed as follows, of two distributions, and I'll explain why in a moment. So it's an integral from 0 to t, p of t minus x, q of x dx. So how do we interpret this? So suppose that we're looking at this time interval from 0 to t. And to accommodate two ticks into this interval, we need to establish some moment, let's say let's call it x, within this time interval, such that at time x we have the first tick produced, and then the rest of the time is dedicated to the production of the second tick. And so then the probability of the first tick happening at time x is q of x. And the probability of the second tick happening in the remaining time, which is t minus x, is p of t minus x. And since these two variables are independent, that we can easily just take like this probability, just count for the probability p as being counted from x, the same as it would have been counted from 0. And then the probability of these two events happening before the time t, so having two ticks at the time t, would be expressed by their product. But then, of course, this time x is chosen arbitrarily on this interval from 0 to t. So in the end, we just have to integrate over all possible choices of x from 0 to t. And hence, we arrive to this convolution integral. Okay, and this was a definition for two distributions, but one can of course also introduce such a definition by induction for n distributions. And I'll just give you the final result, which is that for n exponential distributions, their sum or their convolution, so this can be proven by induction, is the following distribution. Lambda to the power n, t to the power n minus 1, e to the power minus lambda t, which is also called an Erlang distribution. Yeah, so we get this result, and I will not kind of go further in this explanation, but just like in the exercise, you'll have to prove that indeed you get exactly this distribution for n ticks happening at the time t, and then you need to calculate the precision of the clock, which is given by this distribution, and also compare it to the precision r of kind of this one tick, which is 1, and you'll be amazed how straightforward is actually the connection, and that there is kind of another physical explanation of why it's happening. I'll just say that it's a very simple function of n. Okay, so this was the first exercise where we just looked at the one particular example of a clock and the precision of the clock. And but here in this exercise, we don't model explicitly why this is the probability distribution that is governing the ticks. We don't care how the ticks are produced, and so on. So in the next exercise, we'll have an explicit construction of how the ticks are produced, and for that we'll use thermal engine. And we will see what is the thermodynamic limit of clocks. I mean, so the physical idea of this exercise, which is again based on the research paper, the reference as usual can be found in the exercise sheet. So the idea is following that we are trying to ask ourselves a question of, fine, like maybe I can produce, maybe there is a way to produce more and more precise ticks and make the clocks more and more precise. The question is, what is the price that we are paying for it? And is there any entropical price that we pay for a production of more precise ticks. And this exercise and the paper, they answer yes, indeed. And in fact, the precision of clocks is proportional to the entropy of a single tick. But to get to that conclusion, we of course need to model the process of the production of ticks explicitly. And let me start outlaying the setting. So we all
Entropy of a single tick, do you mean the entropy of the probability distribution of one tick?
Oh yes, exactly.
Okay.
But we will in the end not look at the probability distribution itself, but we will look at the how the tick is produced in terms of the thermal baths, and kind of go more into that. But generally, yes, what is usually meant is the probability distribution. Okay, so we'll model an autonomous clock. And we'll associate this autonomous clock with a pointer, which will be driven by heat flow from a hot bath to a cold bath. And the idea is the following. So we have two qubits. One qubit is the hot qubit with the energy gap EH, which is connected to the hot bath at a temperature T hot. So let me do it like this. Okay, and then there is also a cold qubit with the energy gap E cold, which is connected to the cold bath at the temperature Tc. Okay, and so of course these two baths on themselves they form a heat engine, and there is a heat flow from the hot bath to a cold bath. Okay, and then we also have D-level system with equally spaced energy levels. So between two levels, the gap is EW, let's call it. And while the heat engine is working, this heat flow, it drives the state up the ladder of the system. And the idea is that this system is when the state of the system is its highest energy state, the system becomes unstable and the system decays in its ground state. So every time the state reaches the highest point of the ladder, it goes back to the ground state. And in the process of this radioactive decay, there is a photon which is emitted. And this photon goes into the detector, or the detector detects the photon, and that causes the click, so the tick of the clock, essentially. Okay, so this is how we model our thermodynamic clock, let's say.
What kind of physical system would this ladder thing be? Do we care, or?
I mean, yeah, as a theorist, I find this question very hard. No, we don't care. Any physical system, so I guess there are several assumptions I'll about the systems involved, which I'll talk throughout when I explain the setting more explicitly. But the idea is that we just need a system with with a highest excited state, such that it will just with on probability 1 go down to the ground state. So whichever system that allows for that is good.
Do you get it right that there's equidistant spacing between the states, the energy spacing?
Yes, it's equidistant.
Okay, so basically it's like a truncated harmonic oscillator.
Yes, exactly. Yeah, you can use harmonic oscillator for this. Moreover, I guess like you have to use the harmonic oscillator because in the end, to get this bound on entropy, we'll have to take a limit of the number of levels in the system going to infinity. So, like, yeah, again, another theoretical consideration, but yeah, you can use a system with sufficiently high dimension, and also you'll need that the virtual temperature of the cold and a hot qubit wouldn't be too high. So like there would be no spontaneous emission from the ground state, not emission, but going from the ground state to the most excited state. But I'll mention it later.
We assume that only the top state decays to the ground state.
Exactly. So this is one of the important assumptions, because like logically, this process has to be reversible, right? We have to model it as a reversible process, which means that if we model that the most excited state can go to the ground state, there is also a reverse process already encoded in that unitary, which allows for the ground state to go to the most excited state. But we can ensure that this process will almost never happen by making the virtual temperatures such that the probability of this process would be close to 0.
Okay.
Does this make sense?
Yeah, I don't really get why it should be reversible, but there's still decay.
No, so what I mean is that, like, okay, so what I mean is, so suppose that, like, a more easy example. So suppose that you have a qubit, and then you want to describe a process which says that whenever the system is in the state 1, it decays to the state 0. So which means that when you write the unitary for this process, and remember we're in a quantum mechanics, so and the system is isolated, so in the end we have to write all the processes as a unitary. So the unitary would be like it would have a term which would go like this, right? So if the system is in a state 1, it goes to 0. But this is not like, if we just have this this term, this expression will not be unitary. So we need to add the term which kind of also explains the reverse process. So this is just because kind of all the processes that we have to describe, they have to be unitary, which in a sense they have to be reversible, which means that whenever you want to describe a particular process, already in a description of that process, you will have the opportunity for it to go the other way.
Yeah.
Does that make it more clear?
A bit. Yeah, I'll just roll with it.
Okay. Okay, so yeah, again, the idea is that the heat current between these two baths, it just writes the state up this ladder. And as we already seen, I think in the lecture and the previous exercise, like the action of this thermal machine can be equated to the following, which is the resonant exchange between the system, let me call it system V, this ladder, and the virtual qubit. which is formed by these two qubits, like this cold and a hot qubit, like from qubits H and C. And as we've seen in a previous, some exercise sheets ago, like this virtual temperature is given by the following expression. Oh yeah, by the way, here we assume that the energy gap of the hot qubit is bigger than the energy gap of the cold qubit. And of course, that the temperature of the cold bath is less than the temperature of the hot bath. And then the virtual temperature is given by the following. Okay, then what we also need to assume is that the engine ladder coupling so the coupling between the ladder system and this virtual qubit essentially is weak. So which means in this case that the populations of the virtual qubit are always thermally distributed. So we can always assume that the virtual qubit has this thermal distribution at its temperature TV. Or we can also formulate this this assumption as an, oh, every time there is an interaction with the ladder, we just assume that we take we thermalize these two qubits again and use them on U, and so on and so on. Okay. So now we need to come back again to complete our description. So we need to specify how the pointer interacts with the register. And as I already mentioned, when it goes, just to repeat myself, when it goes up to the excited state, it, like with, let's say with probability 1, it goes down to the ground state. And it emits a photon. So let's say excited state, ground state. And in a process, there is a photon with energy, which we label as E gamma, which is d-1 EV, because it's exactly d-1 energy gap from the most excited state to the ground state. Then it's detected at the register and the clock ticks. And as I already tried to explain, another caveat is that when we allow for the photon to decay from the excited state to the ground state, it means that there is also a possibility of the photon being which is in a ground state, not only go to the next state of the ladder, but go to the most excited state directly. But the probability of this happening is low, because we assume that the temperatures involved in the process, like Tc and Th, they're much less than the energy of the photon, or the energy gap between the ground state and the most excited state, which ensures that the probability of probability of the system jumping directly to the most excited state is 0. So yeah, we can write it as Tc Th much less than E gamma. So system V cannot jump from ground state directly to the excited state. So another observation that we can make, which will make our life easier, is that actually the evolution of ladder's energy is probabilistic. And it can be described just as a random walk. So I'm not sure if it was modeled in the lectures. I think it was like the situation where we had to derive the second law in terms of Landauer's erasure, and there we had a model when we wanted to erase a qubit, and we would just have different thermal qubits with different energy gaps, and we would also have a battery where we would store our work, and then in the process, then went, like, we would couple to the thermal qubits each time of a different energy gap, and also store the work in the battery. And then, like, if you would go and model this process that is happening in the battery, where we store this work, or where we extract the work from, you would see that actually it's only the diagonal terms in the density matrix of this battery that survive, and the process there could be seen as a random biased walk, as in, like, there is always a probability of the state going up one or more, depending on which qubit, of course, you use, one or more slots, or down. But these two probabilities are different, which kind of amounts to the random walk. And this is the same thing that's happening here with this ladder system. So at each time we couple this ladder system to the virtual qubit, there is a probability of the state in the ladder going up, and there is a probability of the state in the ladder going down. And these two probabilities are always, or the ratio between them is always determined by the virtual temperature of the qubit, because we assume that, the state of the qubit almost doesn't change during this interaction, so we can assume that it is always at this virtual temperature, and then this jumping on the ladder just depends on the ratio between the probability of going up and going down, or the ratio of populations of this virtual qubit. Yeah, maybe it takes time to convince yourself of this. Maybe you need, like, to write it out. But in fact, like, all the matrices that we would consider here, if we would consider matrices, would have only diagonal elements. But in the end, like, the thought I'm trying to convey here is that actually we can only look at the vector of diagonal elements of this ladder, and then describe the evolution of this vector in time or in steps as a random walk. So what I mean by this is the following. So if we consider this ladder, and let's say that we have the state somewhere in between this ladder, and the levels are equidistant, there is a probability of the state going up, and there is which we label as P up, and there is a probability of the state going down after interacting with the heat engine. And the ratio of these probabilities is given by the virtual temperature by the virtual qubits, and also the energy gap between the levels of the ladder. Okay, and then, as I said, we can just describe the state of this ladder as a vector of probabilities Q of nt, where n is the level of the ladder, and t is the time step. And this is a grid of n integers. And now, given our random process, we can write the evolution of this vector. Of course, sum, like it's normalized, so sum over n q of nt equals 1. Okay, so yeah, again, maybe to connect it, we usually write the same type of equations, for example, for Brownian motion, or actually any random walk. So we have q of nt, and it can go to the next one with a probability p up, can go back with probability p down, and from here it can go here and here, and from next one it can go there and back, and so on. And we have to account for all these terms. And we know also that it can only move one step of ladder down and one step of ladder up. So there are no like more steps that one can do.
Why is that?
Sorry?
Why is that? That it cannot take more than one step?
So okay, so first, because we make our model like this, which is not a satisfactory answer, but the second more physical reason is that we assume that the temperatures of the baths are much less than the energy gap between these two levels which are near each other for this ladder. So just keep in mind that we assume that, yeah, like this one here, this assumption. Which also means that they're also much less than EW, and the probability of jumping from this level to the next level is exponentially higher than the probability of jumping from this level 2 levels up. So in a sense, like we say, okay, we only take into account this event, and for this event, we just assume that it's improbable compared to the first one.
What is E gamma again?
Sorry?
What is E gamma again?
E gamma is the distance, so it's an energy of the emitted photon, and it's this.
Oh yeah, okay, I see.
So it's,
and,
I mean,
do we assume that the probability of going from the top state to the ground state is also P up? Or no?
No, so when so we will go from the state which is up to the state which is down, we assume actually that the probability of going from the most excited state to the ground state is 1.
Okay.
Okay, so maybe just if this intuition is not clear physically, maybe I'll just make a small detour. So again, like this is, let's forget about quantum physics, just usual considerations. So each system that we consider in physics, it has a particular energy scale. So, and for the thermodynamic systems, this energy scale is given by a temperature.
Mm-hmm.
So when we say that that the background temperature is such, like for example, for us, I don't know, background temperature is, I don't know how hot is it now, like let's say 20 degrees. This automatically means that the average energy of the molecules in the air is of the order of Boltzmann constant by this temperature. And so this means that, of course, there is always the probability. So for example, if we want to make the water boiling, like make the water molecules start evaporating, we would need for this to reach this phase transition at 100 degrees Celsius. And one can say, okay, why can't we achieve this transition already at the room temperature? We cannot achieve it because the energy of the current molecules in the air, the average energy, it cannot really achieve this energy energy jump to get to the level when the water molecules would start evaporating and start destroying the energy which binds them to the other liquid molecules. And here it's kind of the same. So when we say that we have this cold and hot background temperatures, this, if you see this ladder as a state of some particle, it means that like to move up the ladder, this particle needs kind of more and more additional inputs of energy. But because the background temperature is that, the inputs of the energy that we can give it are only that much. And so the energy that this particle on the ladder gets are kind of going from that background temperature. And we also know the Boltzmann's law, which means that, which tells us that if we want to increase the energy by delta, the probability of such event happening, given that the average energy like flowing around is like this kBt, it's e to the power minus delta over kBt. So it's exponential, which means that the more energy we want to add to the particle, then the more effort we actually have to make, or not like effort. It's really let's just say that the probability of this event is exponentially decreasing, which in this case means that we can only consider the smallest energy addition that we can have. But this is about the additions, right? When the particle decays, its energy reduces to 0. And when we give energy away as a photon, this is for free. Like the probability of the particle going down is always bigger than the probability of the particle going up. Does it make sense?
Kind of. Yeah. Yeah, sure.
Yeah, so, I mean, thermodynamically, when we talk about thermodynamic calculations, what we mean by temperature on the microscopic level is the average energy of the system that is involved. And of course, when we're driving, and then that's one thing to remember. And the second thing to remember is that the probability of the energy increasing is given by an exponential. An exponential is a very fastly, rapidly decaying function. So
yeah, I just don't get why this like top level is so special that it immediately decays to the ground state as opposed to the other level. But I guess that's kind of the construct of the.
Yeah, this is just for this model. Yeah.
Okay.
Yeah. So this model is very specific. Of course, if you go to the paper and see how they see it, they argue that the conclusion that they made is not model specific, but it kind of should hold for all. But here we just playing around with this engine and just trying to come up with a system which somehow produces the tick, right? in principle, you can define any other event on this ladder which would result in photon emission and producing a tick. It's just like here we choose this one. So maybe like if you have another model, so for example, if you allow for other levels also to decay with some probability to the ground state and produce a tick, then you'll get some other coefficient in your result, or slightly different result, or I don't know what you would get, but like here is just the assumption that we use.
Okay. And something unrelated, this Q is just a probability distribution for some kind of step on the ladder at a given time.
Yes, exactly. So at any time you can describe the system as a density matrix, right?
Yeah, I see.
And it's like these are the elements which relate to the populations of the levels.
Yeah, and I didn't quite follow why it should be diagonal, but it should be.
Yeah, I think for this, like you can also look at the erasure protocol calculations in the lecture.
Okay, I will. Thanks.
Yeah. So okay, so let me just quickly finish this. So we write this change as usual. So this is the portion that is coming from the previous step. This is the portion that is coming back from the next step. And these are the ones that leave this particular point. Then I'll just quickly explain the procedure that you have to follow. Is like you can calculate the mean of this ladder, because in the end you need to somehow identify the event of the ladder being on top, right? So for this you'll need the mean and the variance. And then the next important step is the speed of the ladder. So how fast the mean moves, and I'll just provide you with the answer. And then how fast the variance moves. All right, how it changes with time. And here you actually get that both of them are not dependent on time, which makes integrating much easier. And then we assume that kind of the average time between two ticks which we'll need to calculate the time of the tick. So the average time between ticks is the time for the ladder to travel from bottom to top. So from first level to dth level. And what I mean by this is the time for the mean to travel from first to the dth level. So, and we assume that d minus 1 is approximately d. So we get this here. So this is the time of the tick, like average time of the tick. And then we need to calculate the variance of the average time of the tick. So for this, we just calculate how much the variance has increased during like this mean time of one tick. So I mean, okay, so this is not really nice to write it like this. So we just integrate dt, but because it does not depend on t, we just get by t tick. And then the variance time of one tick can be calculated as sigma at the time t tick over the how fast the mean changes. So we assume that it only depends on uncertainty of at the point when kind of the state reaches the top of the ladder. And then you'll be able to calculate the precision. And then relate it to the entropy change. By expressing P up and P down. Actually, it's only the ratio that will come up there. And the ratio we know is expressed in terms of virtual temperature, which is in its turn expressed in terms of the energy gaps of the cold and a hot qubit and their temperatures. Yeah, and then you need to calculate like during the cycle of this machine, or not calculate, but express like how much heat is dissipated into the cold qubit, given the photon energy. And then you'll see that, and then to take the limit of d going to infinity. And in this case, the precision will be s delta s tick over 2. Okay, so I know this was too fast, but the conceptual idea of this exercise is to look at a particular process. Again, this is not a general conclusion. This is just looking at one particular process of production of a tick, a thermodynamic one at that, and arguing how the precision of the clock depends on the entropy change of the system that we use to produce the ticks. And the idea here is that, of course, the higher precision we have, the better clock we have. However, we pay the price of entropy for that, which also entails that like the more precise arrow of time we define, the more entropy we have to spend for it, which kind of also hints at this irreversibility of precise timing, or how in thermodynamics the arrow of time is usually defined by the increase, the process which increases the entropy of the system. Okay, so this was this exercise. Yeah, it's good to remember its conceptual value. I agree that it's a bit yeah, I tried to adapt it as much as I could from the paper. You can still take a look at the paper if some points of this are not clear. Yeah, and yeah, I think this is everything I had to today.